Uber High AP Chemistry, we are beginning a new unit, Unit 9 on acids and bases. So acids and bases are important because they appear in many places in nature and in many everyday applications. So for acids, these would include fruits or foods such as fruits, milk, vitamins, and many others. Industrial products, car batteries use sulfuric acid. Biological processes, your stomach contains hydrochloric acid. Acids often have a sour taste, so think about lemons when you think of an acid. So for bases, cleaning solutions are often basic, or alkaline is the term used. That would include ammonia, sodium hydroxide, those are both bases. Antacids that neutralize acid in your stomach. So bases and acids neutralize each other, which means the acid is no longer an acid and the base is no longer a base. They become something called a salt. Biological purposes such as plant fertilizers. Bases are usually slippery and they have a bitter taste. Think about soap when you think of a base. So acids produce what are called hydronium ions, or H plus or H3O plus in aqueous solution. Bases produce hydroxide ions, or OH minus, in aqueous solution. So just remember, acids produce an H plus, which is essentially a proton. I'll show you that in just a moment, or H3O plus. And the reason those two are considered to be the same thing, I'll explain that as well. That's called a hydronium. Bases produce OH, hydroxide. So acids are a substance that pulls away protons from its electron. The protons are called hydronium ions. So here we have some sort of acid compound. There's a number that we will talk about. And attached to it is a hydrogen atom. So that hydrogen atom it's the proton, which is its nucleus, and the electron, which buzzes around it. And it's covalently bonded to that acid compound. That's generic acid compound I'm showing there. Okay, so that's basically a full hydrogen atom. One proton, one electron. Often in natural chemical reactions, the proton is ripped away from a compound and it leaves its electron behind. So this happens like this. And it gets pulled away. Why did it get pulled away? Because some other molecule attracted it away from its original compound. So at this point, the proton becomes a hydronium ion, H+, or an H3O+, when it attaches to a water molecule. And that's often what happens. That's why the two are considered the same. H+, which simply means a hydrogen without its electron. It's an ionized hydrogen atom, and it's called a hydronium ion. Okay, so that's what's happening in a nutshell in all acid-base reactions, or all acid reactions, is that proton gets pulled away, but it leaves its electron behind. So now the acid compound over there on the left has a negative charge because it has one extra electron to it without the proton that was attached to it. Acids are divided into strong acids and weak acids. The definition of a strong acid is that a strong acid is one in which all of the H plus protons break away from the acid. 100% of them. If you throw, that's hydrochloric acid there, if you throw 100 molecules of hydrochloric acid into water, every single one of them, that H plus, is going to break off. If you throw 1 million of them into water, all 1 million of those H pluses will break off and be attracted to the water molecule. So when a proton H plus breaks away from its acid, it is said to dissociate. So get used to that word, dissociate. It means break apart. Dissociation occurs because the hydronium H plus proton is more attracted to one of the lone pair electrons on the water molecule than to the chlorine. So hydrochloric acid is a strong acid. All HCl molecules in an aqueous water solution will donate their H plus proton to a water molecule. We'll get into that definition of donate here in a minute. So that's what happens in a nutshell. You put hydrochloric acid in water, the proton of that hydrogen atom gets pulled away to the water, but not the electron, so the electron stays behind on the chlorine. So that's a hydronium ion. So it can either be written as H plus or H3O plus. Really, H plus is just the proton. H3O plus is the water molecule with the proton attached. But just kind of get used to the notation that those are treated as exactly the same thing. There's no difference between H plus and H3O plus. They simply are the hydronium that was created by that acid, by giving up its proton and allowing it to jump over to a water molecule. The hydrogen leaves behind its electron. That means that chlorine ion, which was neutral when it had that proton, is now a negatively charged chloride ion because it has that extra electron that the hydrogen left behind. So there's three definitions of acids and bases. The Arrhenius definition: an acid is a substance that produces hydronium H plus or H3O plus, they're the same thing, ions, and a base is a substance that produces hydroxide, OH minus ions. The Bronsted-Lowry definition defines an acid as a proton hydronium H plus donor and a base as a proton acceptor. So it's the same thing for an acid, but it's different for a base. The Lewis definition, which we will never talk about in this class, and generally college freshman chemistry classes don't, other than just to define what it is. An acid is an electron pair donor. Notice you're dealing with electrons in the Lewis definition. It's an electron pair donor, and a base is an electron pair acceptor. But we're not going to talk about that at all. So the Bronsted-Lowry definition is the primary definition used on the AP exam and in introductory college courses. So that's the one we're going to be focusing on. An Arrhenius acid and a Bronsted-Lowry acid are both defined as proton donors. So for example, HCl, hydrochloric acid, plus water produces a hydronium ion, H3O plus, and Cl minus, the chloride ion. The reaction can also be written using the H plus notation for a hydronium ion. So you notice you don't see water included in that reaction on the left side. You simply say HCl aqueous, which means it's in water. And instead of writing H3O plus for hydronium, you simply write H plus for hydronium. The chloride, the Cl minus, remains the same. So it's a little bit of a shorthand notation. I prefer, and the AP prefers, the top notation, the way it's written in the first equation up above. It's more explicit about what's going on chemically. It's really not just an H plus a proton. It really is an H3O plus, where the proton has attached itself to a water molecule. The HCl donates the H plus hydronium ion to the water molecule. A generic way to write this or any other acid reaction is like this. HA plus H2O produces H3O plus A minus. Or HA without the H2O, just aqueous, produces H plus A minus. So we'll talk about what that A minus means. Here the H plus represents the dissociated proton, H plus, and A minus represents the rest of the molecule. So it's whatever the rest of that acid molecule was before that proton pulled away from it, it's whatever that is. And since the proton always leaves its electron behind, the hydrogen always leaves its electron behind, it's an A minus. It's a negatively charged ion, an anion. Here are a few more examples of Arrhenius and Bronsted-Lowry acids. So that's perchloric acid right there. And we're using the shorthand notation. So you notice that it breaks into H plus and then the rest of it, which is the ClO4. And with that extra electron that the hydrogen left behind, it's a ClO4 minus. So here's the generic way of writing that. HA, and then it produces the H plus, and then whatever is left over is the A minus, and that in this case is ClO4 minus. Again, the reason you want to get used to that generic notation is on the AP exam or in any kind of question you might have on this, they may just simply give you some weak acid and there's tens of thousands of them, that you've never heard of and you have no idea what the chemical formula for it is, and so you simply don't need to. You simply write it as HA produces H plus and A minus, because that's what all acid reactions do. Here's another example. Here's the same thing, I'm sorry, but it's written in the more longhand notation, the preferred notation. So it's still the perchloric acid plus water gives you the hydronium and the chlorate ion. So there's the generic HA, and then there's the generic H plus, which is H plus, and then there's the A minus. And here's nitric acid. So you start off with HA, and then it breaks off into the H plus, and the NO3, the nitrate, is the A minus part of it. So that's just the generic way to write an acid reaction. Okay, an Arrhenius base is defined as a hydroxide OH producer. So there you have a sodium hydroxide, and in water we know that from our solubility rules that Na dissolves with anything. So you can look at your solubility rules sheet. So it will break up with that OH to become a sodium ion and a hydroxide ion. According to the Arrhenius definition of a base, a compound must contain an OH that can be dissolved in water. A Bronsted-Lowry base is defined as a proton acceptor. So here's an example. NH3 is a base. It does produce hydroxides, OHs, in water. But how does it do that? It doesn't have a hydroxide attached to it the way NaOH above did. Well, what it does very simply is it reacts with the water to pull a proton away from the water molecule. So that proton jumps over onto the NH3 and makes it NH4. That extra proton. Remember, an element is defined by its proton. So if you just have the proton jump over onto the NH3, you now have another hydrogen, NH4. But it didn't bring its electron with it. It left that behind on the water molecule. So what you have is NH4 with a plus charge. You added the proton but not the electron. And what did that do to the water molecule? Well, before water had 2 hydrogens and 1 oxygen. Now it only has 1 hydrogen and 1 oxygen. Plus it has that extra electron that was left behind when the proton jumped over to the ammonia, so it's an OH minus, and that's what a hydroxide ion is. So again, you're able to produce hydroxides in water with a base, even though the base itself does not have an OH attached to it. According to the Bronsted-Lowry definition of a base, the compound does not need to contain an OH. However, an OH must be produced. But how? In this example, the ammonia, NH3, accepts an H plus from the water molecule. This produces an OH in solution, even though the base, NH3, did not contain an OH. So here's a summary of the two definitions. In both the Arrhenius and the Bronsted-Lowry definitions, an acid is a proton donor. This means that it gives a proton, called a hydronium ion, away to water or another compound in the solution. In the Arrhenius definition of a base, the base must be a compound containing OH that releases OH minus, AOH minus, a hydroxide ion, into aqueous solution. In the Bronsted-Lowry definition of a base, the base can accept a proton from water or another compound to create an OH hydroxide ion in the solution. Anything that produces an OH minus in solution is a Bronsted-Lowry base. So a Bronsted-Lowry base accepts the H plus hydronium ions released by the acid. In this example, water acts as a base by accepting the H plus ion donated by the HCl. The proton attached to the water produces a positively charged H3O ion. An H plus ion is the same as an H3O ion, so just remember that. The two are exactly the same thing and are called hydronium ions because the proton immediately attaches to the water molecule It doesn't just swim around in the solution by itself. In other words, when that exchange takes place, the water molecule really isn't separated the way it's shown in this image here. It's right up against the hydrochloric acid molecule, right up against that H+, that H, and it just basically hands it over. The Cl hands it over to the water molecule. It doesn't really go across the solution to get there. And that leaves a chloride ion, which is a Cl- ion. So there's the hydronium ion right there. Okay, when the H+ proton is pulled away from the Cl-, it immediately attaches to the H2O. So H+ and H3O are both referred to as hydronium ions. Again, I'm repeating this because it's really important that you get that concept down. So there you go. You can call that either H+ or H3O, but in this class we're going to call it H3O because that's what it really is. It's really a water molecule with an additional hydrogen. AP standards prefer this symbol for hydronium. A strong acid is one in which all of the H+ protons in the acid molecules break away from the acid. In other words, 100% of them. If you put 100 hydrochloric acid molecules in water, 100 of those will dissociate. If you put a million will dissociate. Every single one dissociates. There are 7 strong acids, and you should memorize these: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, perchloric acid, and chloric acid. Some references don't list chloric acid. Some consider it to be a very strong, weak acid, but your textbook does list it as a strong acid, so we'll put it here. So all strong acids completely dissociate in water. All the time the hydrogen will break off and jump over to a water molecule. All other acids are weak acids and do not completely dissociate. So the reason you memorize the strong acids is because if you see an acid and it's not one of those 7, then you know it's a weak acid and therefore has different properties than a strong acid. There are several other ways acids can be classified. So here's the 7 strong acids again. So go ahead and list those. So the first 3 are called binary acids because they contain 2 atoms, 2 different elements, and that's called a binary acid. The ones down below you'll notice all have oxygen, and they're called oxyacids. Acids with more than one hydrogen, such as H2SO4, are called polyprotic acids. Polyprotic means many protons. And what will happen is sulfuric acid is a strong acid for the first of those 2 hydrogens, the first of those 2 protons. 100% of those hydrogens will break away. Then it leaves it with a second hydrogen behind. That's going to be a weak acid proton. Only some of those will break away from the molecule. When the proton from HCl is dissociated from its acid, it leaves behind a chloride ion. A negatively charged ion can attract an H+ hydronium ion, making it a base. So once the H breaks away from the chlorine, the chloride, the Cl- should be able to attract a positive proton back to it. What remains behind is a negatively charged chloride ion, Cl-. So that negative charge should be able to attract anything with a positive charge. The hydronium ion, in the absence of any other substances, attaches to the lone pair of a water molecule to become H3O+. A base that differs from its acid by exactly 1 proton is called a conjugate base. So the conjugate base of hydrochloric acid, HCl, is the chloride ion, Cl-. There's exactly 1 proton difference between HCl and Cl-. So those are called a conjugate acid-base pair. And the importance of those will become apparent when we start talking about buffers and buffers of acids. Then those use conjugate acid-base pairs. So just know the definition for now. When the proton from HCl is dissociated from its acid, it leaves behind the chloride ion. A negatively charged ion can attract an H plus hydronium ion, making it a base. So Cl minus ion is the conjugate base of HCl. The hydronium ion, in the absence of any other substances, attaches to the lone pair of a water molecule, becoming H3O. In other words, if there's a hydroxide, an OH in the solution, then that hydronium could and likely would attach to the hydroxide. In fact, it always will. So a base that differs from its acid by exactly one proton is called a conjugate base. Again, being somewhat repetitive in this slide presentation to reinforce these points. Cl minus is the conjugate base of HCl. A conjugate acid-base pair are an acid and base that differ from each other by exactly one proton. Examples of acids and their conjugate base: hydrochloric acid. HCl is the acid, the conjugate base is the chloride ion, Cl minus. There's a difference between those two of just that one proton. Nitric acid, HNO3, you take away that H, and then you have the nitrate ion, and that's NO3 minus. So they differ by exactly one hydrogen, or one proton, or one hydronium. Acetic acid, that's a weak acid, CH3COOH. You take off the H, and you end up with the acetate ion, CH3COO minus. Those are conjugate acid bases because they differ by just that one proton. The importance of conjugate acid-base pairs will be seen later on. A conjugate acid-base pair are an acid and base that differ from each other by exactly one proton. Examples of bases and their conjugate acid: ammonia, NH3. If you add a proton to it, if it pulls one away from a water molecule, it becomes NH4, and that extra proton gives it a positive charge, so it's NH4+. That's called the ammonium ion. Bromide, Br minus. If you add a hydrogen to that, it becomes hydrobromic acid. That's HBr. There's a difference between those two of exactly one proton. Chlorate, ClO4 minus. You add a proton to that, it becomes perchloric acid, HClO4. The importance of conjugate acid-base pairs will be seen later on. The strong acids completely dissociate in water. This means that every strong acid molecule that enters water will give a proton to a water molecule. So here we have hydrochloric acid entering water. Hydrochloric acid is a strong binary acid, so it passes that proton over to the water molecule. Of course, as I mentioned earlier, what's really physically happening is the water molecule is right up against that hydrochloric acid, and it just kind of hands off that proton over to the water molecule. It doesn't fly across the container of water, the beaker of water. Okay, so all HCl molecules donate a proton to a water molecule. So we're going to repeat this for all the strong acids just to reinforce the concept of acid and which ones and what the strong acids are. So here is hydroiodic acid, HI, strong binary acid. The proton goes over, leaves its electron behind. The hydrogen leaves its electron behind, so just the proton goes over. All HI molecules donate a proton to a water molecule. Water acts as a base because it accepts the proton. Okay, hydrobromic acid. Hydrobromic acid is a strong binary acid, HBr. The proton goes over to the water molecule. All HBr molecules donate a proton to a water molecule. This is nitric acid. It's an oxy acid. Okay. Nitric acid, HNO3, donates that proton over to the water molecule. All HNO3 molecules donate a proton to a water molecule. Sulfuric acid has two protons. H2SO4. It donates 100% of the time. It donates one of those protons to a water molecule. 100% of the time when you throw a sulfuric acid molecule into water. All H2SO4 molecules donate a proton to a water molecule. Sometimes the other H plus hydronium will dissociate and jump onto a water molecule, but not very often. It's a weak acid. That second H plus is a weak acid. The first one is strong and always happens. Finally, we have perchloric acid, Alright, so perchloric acid, HClO4. Proton jumps over there. All HClO4 molecules donate a proton to a water molecule. And chloric acid. That's one less oxygen to it. So that's HClO3. There it goes. All HClO3 molecules donate a proton to a water molecule. Again, that one's kind of iffy. It's could be considered a very strong weak acid, but your book treats it as a strong acid, so that's what we're going to say is happening there. Alright, so what determines the strength of an acid? The strength of an acid is determined by how many hydronium ions, H3O, it places in solution per mole. In other words, per equal amount of acid. So a weaker acid will only have a lesser number. The stronger acid on the right will have a greater number. You can get more H3Os in solution if you use a whole lot of a weak acid and a very small amount of a strong acid if you just want to count how many H3O hydronium ions you have. But the strength of the acid, strong acid, given equal amounts of a strong acid and a weak acid, the strong acid is going to put more hydronium ions into the solution. Okay, logarithms. You've seen these slides before. Why do we use them? Because we will be using them here with acid bases. It's nothing to be afraid of. It's very limited. You really just have to know how to plug a number into them and get an answer and know when to use them. There's just a couple of basic log principles we're going to deal with. So why do we use them? One, they linearize, make a straight line out of curved exponential functions so that analysis becomes possible. And two, they scale down outputs from an exponential function to make graphing possible. So here's a graph of an exponential. An exponential is an equation that has a variable as its exponent. So in this case, y equals 10 to the x. So if you plug in values of x from 0 to 5, you end up with values of y from 1 to 100,000. Well, you can see that would be very difficult to graph that. With a range on your output values of 1 to 100,000, how do you graph that? Whereas if you decided instead of graphing y equals 10 to the x, you graph y equals log of 10 to the x, then each value x from 0 to 5 simply translates into a value of y from 0 to 5. So that becomes very easy to graph. So the graph 10 raised to the x, if you plot that exponential, the graph increases so quickly it won't fit on a piece of paper. And if your computer is the same size as mine, as you're looking at this video, if you extended this graph to x equals 10, that means 10 to the 10th. Given that it looks like 0 to 10 is a little bit about 1.5 inches, maybe almost 2 inches, then that means that red line would extend past the moon. That's how fast that exponential grows. Whereas the graph of log 10 to the x, where it was simply 0 to 0, 1 to 1, 2 to 2, 3 to 3, and so on, you can see that forms a nice straight line, and it's easily graphed without going off the graph paper. So that's why we use logarithms, those two reasons. So now let's get into the pH scale. You've all probably heard of the pH scale. Maybe didn't really totally understand what it was, except it had something to do with acids. So the pH scale is a way to measure the concentration of hydronium ions. Remember, concentration of hydronium ions is what makes an acid. The more hydronium ions, the stronger the acid. And it gives a way to measure the concentration of hydronium ions that's easy to read and to understand. So the concentration of H3O plus ions in water solution is usually very small and is expressed in scientific notation. So example, the concentration of hydronium ions in 1 molar acetic acid, that's vinegar like you have in your kitchen, is 4.2 times 10 to the negative third. Again, a negative exponent does not mean a negative number. It's a positive number between 0 and 1. It's what you call a decimal. Okay, so in this case it would be 0.0042 would be that number in standard decimal form. Since the H3O concentration is what determines the strength of an acid, the pH scale was devised to give chemists an easy-to-read scale of hydronium ion concentrations. So the pH scale is a way to measure the concentration of hydronium ions that is easy to read and understand. pH is given by the following formula. Negative log of the hydronium ion concentration. So pH is the negative log of the hydronium ion concentration. So P, the P part of it simply means negative log of. And you could have a P of anything. You could have a P of your age. You could have a P of your shoe size. You could have a P of any number. It just means you're going to take the negative log of that. I'm not sure that those things would be any use, any useful information, but that's simply what that letter. The P actually stands for power. So what it's really saying is the power or exponent of the hydronium ion. So example, what is the pH of a solution with a hydronium ion concentration of 10 to the minus 9? So you simply take the P of 10 to the minus 9, which means the negative log of 10 to the minus 9, and that simply equals a nice integer number, 9. So when you look at 10 to the minus 9, you see two things you don't like. Even chemists don't like to see these things because they're messy. An exponent and a negative sign. So what the negative log, that whole thing about negative log, it's just a way to turn an exponent into a non-exponent, into a regular number, and the negative sign out in front of log is meant to reverse the negative sign on the exponent so that it becomes a positive number. So the log takes the negative 9 out of the exponent, and the negative sign in front of log reverses the negative sign in front of negative 9 to make the number positive 9. So instead of having this, ugly looking 10 to the minus 9, you just got a nice round number of 9. Okay. Similarly, the POH is a way to measure the concentration of hydroxide ions OH- that is easy to read and understand. POH is given by the formula POH equals negative log of the OH- concentration. POH is the negative log of the hydroxide concentration. So what is the POH of a solution with a hydroxide concentration of OH equals 10 to the negative 13th? So you'd simply plug that in. P of 10 to the negative 13th is negative log of 10 to the negative 13th, and that equals 13. Again, done exactly the same way as pH, except you do it with a hydroxide with an OH- concentration. All right. So let's take a look at this. This table shows the molarity and pH of different concentrations of hydronium H3O+ and how they relate to pH. The stronger the concentration of H3O+ ions, the lower the pH. So low pH is acidic, high pH is basic. The way to remember that is A comes before B and 0 comes before 14. So A is the 0 end, B is the base, is the 14 end. All right, so if you look at this, the concentration at the very top of hydronium ions is very, 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 very small, 10 to the minus 14th. So pH of 14 is essentially not an acid at all. If you go down to the bottom, you have pHs of very low numbers, and if you look at the concentrations all the way up to 1 molar, that's a pretty strong concentration of an acid, particularly a strong acid. So that would be a pH of 0. And they can range everywhere in between. A pH of 7 is considered neutral between acid and base, and that's the pH of water. So lower numbers on the pH scale represent stronger acids. So what is the pH of a solution with a hydronium concentration of H3O+ concentration equals 10 to the minus 9? So pH simply equals P 10 to the negative 9, which is negative log 10 to the minus 9, which equals 9. So we saw that example before. So let's practice on some of these. Give the pH of the following hydronium concentrations. So how about pH of 10 to the minus 6? The hydronium concentration is 10 to the minus 6. Then that's negative log 10 to the minus 6. That's 6. pH 10 to the minus 13 is negative log 10 to the minus 13. That's simply 13. Again, the log brings it out of the exponent, and the negative sign reverses the negative sign in front of the exponent, so you just end up with a nice whole number. 10 to the negative 2 is 2. 10 to the negative 5 pH is going to be 5. Okay, let's do some with coefficients in front of them, because usually they do have coefficients. So what about the pH of 5 times 10 to the negative 6? So over on the left you have 1 times 10 to the negative 6, and that equals 6. What is 5 times 10? It's going to be 5 times the concentration. So its negative log of that is 5.3. So notice what happened. The concentration on the right is 5 times 10 to the negative 6. That's 5 times greater than 1 times 10 to the negative 6 on the left. And notice what happened to the pH. It's a stronger hydronium concentration, so the pH went down. It became more acidic. As it becomes more acidic, the pH becomes lower. So it went from 6 down to 5.3. Okay, how about this one? pH of 3.2 times 10 to the negative 13. Take a guess at what you think that'll be. You see over on the left that 1 times 10 to the negative 13 is 13. Now you've got a higher concentration of hydronium. You have 3.2 rather than just 1 times 10 to the minus 13. So what's that going to do to the pH? Plug it into that, and you get a number that's less than 13. In other words, it's moving in the acid direction. It's moving in the direction of lower number pHs, which is acid. Okay, do a couple more so you can kind of guess what the pHs will be. The pH of 1.25 times 10 to the minus 2. So you plug that in, and you get 1.9. Okay. And finally, let's do one more. pH of 8.9, 1 times 10 to the minus 5. Plug that in, and you get 4.1 for the pH. Okay, so you compare those. The 2 to 1.9, it went down. That means it's a stronger acid. The 5 to the 4.1, it went down, so it's a stronger acid. Okay. All right, let's keep going. Right, by using the properties of logs, we can compute the concentration of H3O ions from pH. In other words, going in the other direction. Remember that log base 10 and 10 raised to a power are inverses of each other. So what we're doing is we're using the inverse. If you don't remember that from math class, we talked about it in about lesson 2, way back at the beginning of the class. So go back and review some of the properties of logs. So if we want to know the H3O plus concentration and we know the pH, you simply take 10 and raise it to the negative pH. And that will give you the actual molar concentration of hydronium ions. So example, placing the pH equals 9 obtained in the previous example, we can compute the H3O plus concentration we began with. So it's simply 10 to the minus 9. That's what you do. You just take 10 and raise it to the negative of the pH. And that's the pH, that's the hydronium ion concentration we started with when we got pH equals 9. So we just went backwards on this. Okay, an important concept in the study of acids and bases is the autoionization of water. The word auto means self. So autoionization means a small fraction of water molecules naturally break themselves apart into H plus and OH minus ions. The reaction for this process is H2O into H plus and OH minus. So notice what you're doing is you're breaking a water molecule in two, not in half, but in two. You're taking H2O, you're pulling one of the protons away from it. That basically is one of the hydrogen atoms, but it's leaving its electron behind. So now instead of having two H's and an O, you have only one H and an O, plus that extra electron, which gives you an OH minus. And then going over somewhere else is the H plus, that hydronium, and that's going somewhere else. So this is a very simple reaction. So when this happens, the ionized water molecules recombine back into H2O. It's roughly, it's a very, very small number that do this at 25 degrees. And whenever you see one of these problems, anything with an acid base, it's always at 25 degrees, which is room temperature, unless they tell you otherwise. But it's virtually always going to be 25 degrees. So at 25 degrees, a very small number of water molecules autoionize like this, and when they do, they immediately come back together. I mean, what happened? It's just through some kind of fluke circumstance, another water molecule was able to pull a proton away from its original molecule, but then it doesn't want to stay there very long because it's not very stable, so it jumps back onto its original molecule. It doesn't happen very much, but it's constantly happening with different water molecules. It's not all the same water molecules doing it. So other water molecules then autoionize. This makes the autoionization of water a reversible reaction and an equilibrium situation. And if it's an equilibrium situation, you know what that means. That means you can write a law of mass action for this reaction. Okay, so at 25 degrees, the concentration of H3O plus ions is about 10 to the negative 7th molar. Okay, that means 10 to the negative 7th moles per liter. And a liter of water is about 55.5 moles. So you have 10 to the minus 7th. That's 1/10 millionth of a mole compared to 55 moles of water. So it's a very, very small amount in pure water. Since each of these broken water molecules also produces an OH, this makes the OH concentration also 10 to the minus 7th molar. So you have a water molecule, and every time you end up, it autoionizes into a hydronium H+, it's also got to autoionize into an OH-. So you always have the same number of H+ as OH- at any time. So there is the formula. So since this is an equilibrium situation, it has a law of mass action equation, which is that. Look at that and convince yourself that the Kw, that's the equilibrium constant for water, is equal to that. It's the product side over the reactant side. So the products, you have hydronium and OH in aqueous solution. On the reactant side, on the left, you have water, pure water. But if you remember, you don't include pure liquids or pure solids in an equilibrium law of mass action. So all it is H+ and OH-. So Kw is called the water dissociation constant. And at 25 degrees, this is a key number to remember, Kw is 10 to the minus 14th. Look up at the law of mass action. If H+ is 10 to the minus 7th, which we said it was up above, and if OH- is also 10 to the minus 7th, which we said it was up above, then Kw is going to be 10 to the minus 7th times 10 to the minus 7th, which is 10 to the negative 14th. And that's the dissociation constant of water at 25 degrees, and that's the one you're going to use in all the problems that we're going to do. So we learned that at 25 degrees centigrade, water molecules autoionize to produce the following law of mass action for the autoionization of water. This means that if we know the hydronium concentration, we can calculate the hydroxide concentration, OH, at 25 degrees centigrade, and vice versa. You can do in the other direction as well. Example, what is the hydroxide concentration of a solution with a hydronium concentration of 10 to the minus 3? So you simply take that equation, Kw equals concentration of H times concentration of OH. You have to solve it for OH, so divide both sides by hydronium concentration, and that gives you Kw over hydronium concentration, which is 10 to the 14th over 10 to the 3rd, which equals 10 to the negative 11th. So that's the hydroxide concentration in the solution. Okay, now this simply adds on to the table we saw earlier. It has the same numbers for the acid over on the left and for pH, but on the right we've now added the base concentrations and the pOH. So you can see it's exactly the same except it's flipped around. Okay, so if you have a pH of 14, you have a pOH of 0. And that's a very strong base, in other words. It's only 10 to the minus 14th molar for acid, but it's 1 molar for base, so it's a very strong base. And as you move down the table, the bases get weaker and the acids get stronger until you get to the bottom. So you can just kind of see how all of that relates right there. Okay, there's another relationship we can derive from this formula that we just came up with. We take the negative log of both sides. So we take the negative log of the hydronium concentration and the hydroxide concentration, and we go over, and we're assuming we're at 25 degrees, we're going to take the negative log of the Kw, which is 10 to the minus 14th. Now, one principle of logs, you don't have to really remember this, but it's that if you take the log of two terms multiplied together, it's the same as adding the log of one of the terms plus the log of the second. So just look down there. So negative log of H plus times OH minus is equal to negative log of H plus negative log of OH minus. That's just simply a principle of logarithms if you remember from your math class. I think it's also back in lesson 2 that we mentioned this. Then you also continue to take the negative log of the right side, 10 to the minus 14th. So what does negative log mean? What does that mean? What did we just learn negative log means? It means P. So we can write everything in P form. So that means pH plus POH equals 14 at 25 degrees. So that's another really nice relationship to know if you're converting from pH to POH. So here's a summary of all the equations we talked about. To go from the hydronium concentration to pH, it's 10 raised, to get the hydronium ion concentration from pH, you take 10 and you raise it to the negative pH. To get the pH from the hydronium concentration, you take the negative log of the hydronium ion concentration. To get the hydroxide ion concentration from POH, you raise 10 to the negative POH. And to get POH from the hydroxide ion concentration, it's the negative log of the hydroxide concentration. And then the one that gets you between acid and bases here is this one of them, there's 2 of them. The relationship between hydronium concentration and hydroxide concentration is that hydronium concentration times hydroxide concentration equals 10 to the minus 14th. Again, that's at 25 degrees, which we're going to always assume unless you're told otherwise. Finally, the relationship between pH and POH is pH plus POH equals 14. So what I'll be doing is giving you some problems that deal with these relationships so that you get comfortable moving around between these. All right, so here's kind of a roadmap to show you these relationships. So let's look at the top. If you have hydronium concentration and hydroxide concentration and you want to get between them in one direction or the other, it's just H plus times OH minus equals 10 to the minus 14th. Down at the bottom, if you want to get between pH and POH, it's just simply pH plus POH equals 14. And then over on the left side, to get between hydronium ion and pH, it's just either 10 raised to the negative pH to get up to the hydronium, or to get down from hydronium to pH, it's negative log of hydronium concentration. Same thing over on the hydroxide side, the base side. To get from hydroxide concentration down to POH, it's just negative log of the hydroxide concentration. And to get from POH up to the hydroxide concentration, it's 10 raised to the negative POH. So we'll finish up this lesson with a couple of problems. Okay, so what is the pH of a solution where the hydroxide concentration is 3.2 times 10 to the negative 4? So you're trying to get down to pH in the lower left corner down there, and you're starting up in the upper right corner with hydroxide concentration. So you can see there's 2 paths you can take. You can go across and then down, or you can go down and then across. So let's try both of them. So we're first going to go across from OH over to H3O plus. Get that, and then we're going to go from H3O plus down to pH. Okay, so the first one is, you have to solve for the H plus, which is H3O plus concentration. That's 10 to the minus 14th kW over the OH concentration you were given, and that gives you 3.13 times 10 to the minus 11th for the H3O plus concentration. Now you're going to go down and to get from the H3O plus concentration to the pH, it's the negative log of 3.13 times 10 to the negative 11th. And when you solve that on your calculator, you get 10.5. So that's a pH. That OH concentration they gave you at the beginning, 3.2 times 10 to the negative 4, is equivalent to a pH of 10.5. Let's try going in the other direction. So we start at the same place. Now we're going to go this way, down from OH to POH, and then across from POH to pH. So going down, we have the negative log of the OH concentration, gives us a POH of 3.49. Then once we know the POH, we can use the formula pH plus POH equals 14. So that's going to be 14 minus the POH, 3.49, will give you the pH, and that equals 10.5. So we get the same answer going in either direction. Okay, let's do one more, and then I'll introduce you to the acid-base roadmap in your reference sheet section. Okay, so I think that's, whoops, there we go. Yeah, okay, so what is the hydronium concentration of a solution where pOH is 8.7? So you're going to start down in the lower right-hand corner at pOH, and you want to end up in the upper left of H3O. So that means you take your pOH of 8.7 and subtract it from 14, and that gives you the pH of 5.3. Now you take the pH and you make it an exponent of 10, so 10 raised to the negative pH. So there it is right there, 10 raised to the 5.3, and that equals 5.0 times 10 to the negative 6th. So that's the hydronium ion concentration that you get. Okay, I want you to talk to you about the acid-base roadmap that's in your reference sheets section before we conclude this lesson. Okay, so this is the acid-base roadmap, and while it looks a little busy at first, you're going to take it one piece at a time and learn different pieces of it, and eventually it's going to give you a lot of information that you need to solve acid-base problems. So let's take a look at what we did today. You're not going to need all of this sheet today. So if I go up here, and if I'm just going to cover this over temporarily in red, there you see the conversions between hydronium concentration and pH. So to go from hydronium to pH, it's negative log of hydronium. To go in the other direction from pH, it's 10 raised to the negative pH. So that's two that we talked about. Now we can go over to the other side and see the same thing for hydroxide. Okay, so if you want to go from the hydroxide concentration to pOH, it's the negative log of the hydroxide concentration. You go in the other direction from pOH, you take 10, raise it to the negative pOH, it'll give you the hydroxide ion concentration. And then finally we saw how do you get from acid-base on the left, what we just talked about, to hydroxide right here. It's these two down here. Those are the two that bridge between acid-base over on the left, H plus and pH, and base, acid on the left, H plus and pH, and base on the right, which is pOH and OH minus. And those are the two equations that tie those together. The K, the ones involving K, we'll deal with at a later time. You also see a list of the strong acids over on the left. We didn't really talk about strong bases as much. We will talk about those as we get more into a little bit more, but the strong acids are really the ones you want to memorize, at least for right now. Okay, and everything you see down below, it's nothing to really think about too much at this time. All right, so that takes care of this lesson on basic acids and bases. So work these problems. I didn't give you a lot of problems, and they're not really long. I did give you some question and answer because I need to be sure you understand the concept of what an acid is, what a base is, okay, and the definitions of acid and base. All right, so I'm going to leave it at that, and we'll head back here. Okay, so that takes care of our lesson on basic acids and bases. mainly dealing with strong acids and just the general concept of acids and bases and how you compute pH and pOH. We're going to deal with weak acids on Monday. They present a little more complicated situation because they don't go all the way from 100% from acid to dissociation to in water. So it's an equilibrium situation where they stop somewhere in the middle. All right, so get this lesson done. I'm keeping it kind of short. Be sure you understand the definitions of acid base and how to compute pH and concentrations and pOH, and that'll do it.